Alright, so for the pre-lecture video for day 8 of class, I'm going to talk a little bit about electric potential, but then sort of concentrating on the idea of equipotential lines. So the electric potential derives from the desire to sort of eliminate the charge that we were using to define potential energy. So remember that when we look at electric potential energy, what's happening is we're looking at the interaction of a charge with an electric field. But we would like to take the charge out of that and really get some information about the electric field alone. And basically that's what electric potential allows us to do. If we think about the charge in the electric field as Q naught, then the potential is equal to the potential energy over that Q naught. So potential, in its definition, is the potential energy per unit charge. It's going to be measured in volts, which should sound familiar to you because you've seen batteries are measured with how much voltage they have. You've seen that term probably a lot of different places. So let's look at the electric potential. We're going to start off with the idea that, where we've been beginning a lot, that work is equal to the force on a charge in an electric field dotted with the displacement. And we found that that was related to minus the change in the potential energy. So if we use the idea that potential is potential energy per unit charge, then it makes sense to say that the change in potential is equal to the change in potential energy per unit charge. So all that we've done is we've gone from just a value of these two terms, potential and potential energy, to the change. And using then our definition of work up here, we could say that it's equal to minus the electric field dotted with the displacement. And so what we're seeing is that what this is telling us is as we move around in the electric field, we're going to see a change in the potential. And the negative sign will actually mean that as we move, if we move with the electric field when we're moving around, then we're actually going to see a decrease in the potential energy. So potential changes as we move in an electric field. If we move with the electric field, the potential is going to go down. And so here we see that represented in this picture. If we are moving out parallel to the direction of the electric field, our potential value is going to decrease. And of course then if we move in the opposite direction of the electric field, the potential is going to increase, sorry. Sorry. Potential will increase as we go inwards. So what potential is it gives us a sense of a measurement of the electric field, which in the end we can also go back to the idea of energy, because we can think about as we move around in the electric field, we're going to encounter or experience changes in potential, which then if we take a charge through those changes in potential, that charge will experience some sort of change in potential energy. It seems a bit circular, but it is a useful term to be aware of. And here is the picture, here's the relationship again. Unfortunately, when I use this program, it doesn't do subscripts. So what we want to say is UA minus UB is equal to Q VA minus VB. And so this just comes from the definition of the fact that the change in potential is equal to the change in potential energy over charge. And so they've just rearranged it so it says that the change in potential energy is equal to the charge times the change in potential. And so basically it's saying is if we take this charge and we move it through this change in potential, delta V, then the change in the potential energy that the charge will experience is going to be this value. Now, you might have heard or read in the book they talked about electron volts. Let me just skip back up here a minute and say that the potential energy, in terms of the way that we measure it, it's going to be measured in units of energy. And so the unit of energy that we're familiar with is joules, and so that's still going to apply. Because of the idea or the relationship between potential energy and potential, and the fact that we're moving charges through some sort of change in potential, there's another way that we can express the energy change that the charge will have, and that unit is called an electron volt. And the way that it works is it's actually a lot easier to calculate the energy when you use electron volts, because we think of the charge measured in units of the charge of an electron, and then this of course is measured in volts. And so then if you take an electron or something that has a charge equal to an electron or some multiple of electron charge, and that means we're not expressing it in coulombs, we're just saying it has a charge of the electron, or the electron is the thing that's moving through a certain change in potential, which of course will be measured in volts. The value is simply the electron volts, is the change in potential energy. So if we have one electron and the change in potential is 5 volts, the change in potential energy will be given as 5 electron volts. This is a conversion factor between electron volts and joules, which is sometimes useful to know. Notice that the conversion factor, and this should be superscript, is just the charge of an electron, and that should make sense. All right, so now that we talked about a potential, you might kind of wonder, how do we know what the value of potential is at a particular location in an electric field, and how do we know how much it's going to change? And so we have this idea of equipotential lines, which is simply lines along which the potential is constant. So we found that the change in potential could be expressed as minus the integral of E dot ds. And so we're going to use this definition to help us figure out what an equipotential looks like. If we move along an equipotential, it means that we're moving along a surface where the potential always has the same value, and that means that delta V will be equal to 0. And so we have to think about how this calculation would yield 0. And so we're looking for a time when E dot ds equals 0. And remember, this is a dot product. So when we take the dot product of two vectors, is their dot product equal to 0? And that's true when the two vectors are perpendicular to each other. And so this helps us figure out what the equipotentials are. The equipotential lines or surfaces, if we're thinking about 3 dimensions, are perpendicular to the electric field. Oops. So if we look at this picture of the electric field lines, these are the E field, we see that these blue circles represent equipotential lines. And of course, they're always drawn perpendicular to the electric field. Notice also that the values of these equipotentials increases as I move towards the charge, which is in the opposite direction of the electric field, or vice versa. If I move from the charge outward in the direction of the electric field. Remember, that's the direction of decreasing potential, and we see that the equipotential lines have decreasing values. Now, from our definition, remember that we said delta V is equal to minus E dot ds, and it's equal 0 along equipotential. Remember that this is related to the work. It's really related to minus the work over the charge. And so we're also saying that it doesn't take any work to move a charge along an equipotential line. If we use the definition or the analogy of a hill, really moving along an equipotential line is sort of like an object moving along a level surface. It doesn't really take any work to make it go anywhere. That's sort of a loose analogy. Now, some of the applications, like if we think about, okay, we learned some things about conductors that are in electrostatic equilibrium. So let's say that we had a conducting sphere, and all the charge, of course, is on the surface, and we know the electric field is 0 inside. And so we might ask, as we're moving from one point to another within the sphere, what does that mean about the potential? Well, let's look at this. So what happens is that if we move around within the sphere, because there is no electric field, our potential doesn't change. But the fact that the change in potential is 0, what doesn't tell us that the potential has to be 0. This doesn't mean necessarily that V equals 0. What it means is that V isn't changing. It has a constant value. So what we end up actually figuring out is then the potential within the conductor, when the electric field is 0, has a constant value. Not a 0 value necessarily, but a constant value. And so when we look at this, we see that it has a constant value, which is going to be equal to whatever the potential is on the surface, because we have to have some sort of continuity, and then of course it'll drop off as we move away. Finally, we're going to use this relationship to find a relationship between the potential and the electric field. So again, we have this, delta V is equal to minus E dot ds. For the simple case, let's E be equal to EX in the I direction, and then of course ds, let's let it be equal to dx in the I direction. And so delta V is equal to minus EX dx. And if we take away the integral, this just makes dV equals minus EX dx. And we can actually then rearrange this. And we can, if we know what the potential is, we can actually calculate the electric field. by taking the derivative. I think that you saw something really similar in first semester where we actually were able to find the force was actually related to the change in the potential energy. So this is similar. And then we also, in that situation, made it a little bit more general, where we could look at cases where we looked or moved in different directions if we had the possibility of a component in the x and the y and the z direction. These derivatives turn into partial derivatives because we're only looking at how it changes in the respective direction. And so this allows us, given an expression for potential, another way to find the electric field.